Good afternoon, everyone. First of all welcome Dr. Santosh Kumar Sahu and all the participants who could find time to join this meeting. So, Dr. Sahu would be speaking on carbon productivity in the Indian manufacturing sector. But before we get into the topic, let me again talk about this DST Center for Policy Research. In India, we had in the past only three Center for Policy Research funded by DST, and one at IISc Bangalore, second was at IIT Delhi, and third was at Punjab University. And DST wanted to basically expand this Center for Policy Research to different regions, and so they actually had a call for proposal, and we submitted, and then we are now here. So we got it, and so our focus will be on eastern part of India, and we'll be looking at two issues broadly. One is on energy transition, and second is on tribal education. And now we are holding a number of lecture series. So there are two reasons. One is that first of all, we need to understand the challenges involved in the energy transition, and the second is to also build up a network. Okay? So with that objective, we have started this lecture series, and this is the third one that we are organizing, and we are doing this online so that people, whoever is interested, to participate in this event. And we had actually two earlier lectures. So today, Dr. Santosh Kumar Sahu, who is working at IIT Madras, would be basically giving this lecture. So I really thank Professor Sahu for accepting my invitation, and he kindly agreed to deliver this talk. And recently, in fact, they have started a sustainability center at IIT Madras. So, Dr. Sahu had shared that event, that YouTube link with me, and I have watched the entire thing. And so I really congratulate the entire team at IIT Madras, who have taken up the sustainability issue very seriously, and they're going beyond actually these disciplinary boundaries, and they're bringing different disciplines together and doing collaborative research. So to introduce Dr. Sahu, Dr. Santosh Kumar Sahu is an associate professor of economics in the Department of Humanities and Social Sciences, and associate faculty at the School of Sustainability at IIT Madras, Chennai. His research interests include energy economics. One minute. Yes, his research interests include energy economics, applied microeconomics, industrial economics, institutional economics, and the economics of global climate change. He is also an affiliated researcher at the Center for Technology and Policy, IIT Madras, and Energy Consortium, IIT Madras. He received the Trendsetter Grant Award, Australia Awards Fellowship, and Professor Raghuram Rajan's Young Scholar Grant Award. So Dr. Sahu, if you look at his publication list, he has a long list of very good or excellent publications in very reputed journals. So with that brief note about Professor Sahu, I now invite you to deliver your lecture. Over to you, Professor Sahu.
So thank you, Professor Das, for the invitation. In fact, it's a wonderful feeling that DST has interested to reach out Eastern India to have studies on both important issues. One is on energy, second is on the tribal, economic, political, and development issues, where NISER is greatly helping the government of India on creating a policy cell where you are heading the cell. So, which is wonderful news. As a part of the energy transition talk series, I'm really happy to be here, invited by you and the institution of yours. This research is basically, this is my ongoing research that currently I'm involved with, Energy Consortium IIT Madras, which is one of the group of scientists, economists, and engineers who are trying to understand and come up with solutions for energy efficient solutions and carbon efficient solutions. So the title of the topic today that I'm going to present is on carbon productivity in the manufacturing sector of India. It's an ongoing study where we are trying to look at from the secondary data perspective, where we have few verticals. One is on the methods, methodology, and techniques. Second is on the data quality, and analytical tools. And third is the perspective of creating a new data set in future. So as I was telling, this project is currently funded by Energy Consortium, which in the Trendsetter Grant Award that I have received recently. So as a mandate of the program, we have to periodically work, and I'm really happy that I'm presenting this work in front of the audience, where energy neutrality matters, where carbon and climate change matters. So to begin with, we all know about the fundamental problems with the climate variations and climate change, which started from the Kyoto Protocol of the earlier days to Paris Agreement to net zero targets. So there has been an involvement of international community, the developed world, also called the high income, low income countries, where the role of each countries are different based on how much they emit, based on various other parameters such as the welfare economics of each of the countries to the environmental sustainability viewpoint, which may be looked at from the SDG or MDG goals that we talk about. However, the impacts are different, and there are certain economies where the impact seems to be higher. There are certain economies where the impact seems to be lower. And certain economies have experienced the man-made climate disasters at a faster rate compared to certain other economies. So there has been a big way that there is a heterogeneity in terms of the behavior of the climate that functions, and hence the adaptive capacity or the policies are different for different countries. And as today we talk about technology, we talk about carbon, we talk about sustainable development. We are also talking about welfare of the people, where we are talking about employment, we're talking about the minimum basic needs of individuals. So in such case, what happens? There is a big trade-off that comes, and this trade-off is largely because of the disparity of income and the distribution of income and natural resources in most of the economies. And the advanced economies, advanced in technology or advanced in income, tend to have a larger role to play as compared to the economies which are largely dependent on the resources from these economies, which are largely characterized as high-income countries. So in this case, in economic science, we have the polluters pay principles as one of the foundational goal, or we have the voluntary redistributed agreements between economies, where polluters pay principle seems to be a little rigid and regressive in nature, such as the Pigouvian tax, whereas mutual agreement and voluntary agreement seems to be a better possibility. So in this backdrop, if we look at where India stands, and what India is doing currently to achieve sustainable development goal, become one of the largest economies, best 5 largest economies sustainably from the finance perspective and from the development perspective. If we look at the emission in 2019, and why 19? Because the follow-up years were COVID years, and therefore it is ideally better not to look at the carbon emissions in the COVID year, where manufacturing was at a halt and the production value chain was directly impacted. So if you look at the 2019 data, we account almost 7% of global emissions. But with the 7% of global emissions, we are still able to receive international funds on climate negotiations and climate investments. But that doesn't mean that India as a country is growing on the same rate. We will foster our economic growth. And when we foster economic growth, that is going to depend on the manufacturing sector. And because manufacturing sector obviously has a larger link with creating employment to agriculture and linked with various other sectors. So this 7% of global emission is quite huge, because India is projected to grow faster. India is going to go bigger in terms of industrial activities, and therefore we have to think today how we can look at the energy dependent India economy from a manufacturing sector. And if you look at the manufacturing sector carefully, the data point that we have, then manufacturing sector accounts for, as one of the largest energy consuming and emitting sectors. That is quite a concern, because unless we achieve energy efficiency in the manufacturing sector, the aggregate energy efficiency seems to be a little difficult in this case. And if you look at the majority of the policy that has been in place in last decade, we have encouraged Make in India, we have encouraged entrepreneurship development, Startup India, and a lot of other activities to encourage to boost the manufacturing sector, which are going to be energy dependent sectors. And therefore, it is always better if you can look at the cost effective emission policy. In that sense, what happens, we become sustainable in one way, and also we become cost effective. And the third question is equally important: we may become energy secure, because India is one of the highly energy importing countries along the world. But then the question is, why suddenly we talk about carbon productivity? Because usually the neoclassical framework of economics or applied industrial organization and industrial economics, or microeconomics for that matter, try to talk about productivity. And till today, people are working on productivity dimensions, because yet to be discovered the way the entire industrial system is changing. But then suddenly, why we must think about carbon productivity? Because that's one of the measurement issues that comes in terms of a comparison when we try to tax it, or when we try to come up with any monetary or fiscal measurement in terms of regulating it. And this is one of the effective ways to reduce carbon emissions while boosting economic prosperity. The simple reason is, if we calculate the carbon intensity, then obviously when technology grows, what happens is we produce more. However, we tend to use more energy services, and hence we emit more. So therefore, what happens, the aggregate emission keeps on increasing, no matter we are going to create new technologies or new production systems. So increase in the aggregate carbon is a concern, and therefore looking at a carbon productivity viewpoint is something that we can get some new results in this case. And obviously, if you look at the existing literature, then we see that improving energy efficiency and reducing CO2 emissions in the manufacturing is very crucial, because the technology involved in the manufacturing sector, may it be small, medium, large, or even tiny industries, are not homogeneous across the country, and there are technological barriers in manufacturing sectors, and we need to come up with efficient production systems so that the natural resources is used appropriately and we get the allocative efficiency in a much better sense. But then when we talk about a new thing, or a new way of looking at a measurement problem, for example, there is a large-scale debate on how to measure productivity in general from a neoclassical point of view. Then the question now is how to measure the carbon productivity, which is even more complex as compared to calculation or computation of productivity itself. So if you look at the existing standard literature on calculating or computing the carbon productivity, there are two strands of literature that comes in. One is from the data envelopment process, data envelopment analysis perspective, and second is from a pure economic perspective. Each of them has their own methodological issues, limitations, and critical thinking. But if you look at the way it has been measured, is basically a growth accounting measurement, right? Now, in the growth accounting measurement, one important indicator of choice or index of choice has been the Malquist L index, which is the ML index, created by Chung in 1997. But the problem with that method is it is infeasibility problem, where it is difficult to allocate the DEM, which is DEM, and then get a better result out of that. So what is the solution to that? The first solution is, can we define a global production possibility set instead of a local production possibility set? Because we are talking about carbon emissions, and when we talk about carbon emissions, it's not boundary specific. So it's a global problem, and it's a global public good. So we are going to be affected if the global temperature is going to go up. So therefore, we are going to be affected in the similar case if the carbon emission goes globally. So can we define a global production possibility set and compare that set with the existing local set? Which is developed in 2010 by the paper that is cited. Or there is a solution too by creating a biennial Malquist index, but the problem in that index is it lacks transitivity. So therefore, what happens? There are measurement issues, and these measurement issues have to be understood from the idea of good product and good output and bad output produced, and then link the good output, bad output each other, and look at the convergence problem. Now, to To continue on the issue of the measurement issues, because in such studies which are not purely economic in terms of using a financial series, but also using series which are stock in nature, because here we are talking about variables which are in stock and variables which are in flow. So the redial DEA method without stack is basically creating a problem of biasness, and therefore we cannot use that. So for the convergence analysis, generally what happens, we are going to use something called a sigma convergence and beta convergence. And based on the sigma and the beta convergence, we try to understand which sector of the economy is converging and which sector of the economy is not converging and which sector of the economy is sustained or there is no growth in terms of the convergence parameter. And this entire understanding of the DEA methodology that is given to understand and explain the bad output from the environmental economics perspective has become a standard approach in this particular case, which is going to help us in terms of policy research. So based on these few methodological constraints, we start this research process. And the objectives are very straightforward at this point in time. First, we estimate emission from farm levels, because as we know that data from farm level emission is not present. We do not have data recorded from the output point of view as an emission, and therefore the only way is to estimate is from a bottom-up approach. That is one objective that we are surrounded with. The second objective is measurement of carbon productivity. So it can be done in multiple ways. And this paper, we're using a DEA approach, and then also we use a convergence approach from an econometric perspective, so that we have a mixed method framework. In doing this, we believe that we will come up with sectors where we have to think about policy change, sectors where we have to come up with incentivizing, and sector probably where we have to come up with tax benefit and something like that. So if you look at the measurement and the theories of carbon productivity, so as I said earlier, we have the global production possibility set, and the GPS can be defined as the following equation, where I have given two different colors. The red color is basically the change that happens within industrial or within sectoral change, which is called a cross-section variations, and the blue color that signifies in terms of the economic of scale and production technology. So if you look at this particular equation here, what is happening is your output, which is a good output and a bad output, is typically explained by cross-section variations and economics of scale and production technology that comes from the neoclassical economics perspective. But then what you can do, you basically can update that, and you can create the idea of unintended output. So what is the unintended output here? The unintended output is the CO2 emissions. For example, a typical manufacturing firm, when produces good A or B, it does not want to produce good C, which is the emission or the CO2 emissions or any kind of emission. So it's an unintended output by the typical company or typical firm. So when you add the unintended outcome, you get a little complex equation, which is represented here as against the equation that you had here, which is basically cross-section variations, economics of scale, and economics of production. Now, once you understand this process, then basically what you're going to do is you use a global stack-based measurement where you create a distance function by creating a local data set where a particular firm is behaving the perfectly efficient parameter, and calculate the distance function from there, so that we know which sector requires specific policy implementation and which sector is leading the frontier. And then what we can do, we can basically divide it, we can basically decompose it in terms of various decomposition techniques, which I'll speak in a minute. But the measurement issue also links how to interpret these data, because these are basically linear programming related stuffs or mathematical modeling, where you need to know how to interpret the series, where you get the growth accounting framework, right? So the GML, which is basically the choice of variable interest here, which will represent the idea of carbon productivity, will get a value between 0 to 1. And this value that is between 0 to 1, if it is equal to 1, it will imply that carbon productivity is same between two periods. It depends on the researcher to think about multi-period, two-period, or decadal growth. It depends on the researcher's point of view. So therefore, it will be n minus k variable kind of a thing, where you basically compare between period 1 and period 2, or you can keep on comparing across periods. Now, if the decomposed value if the GML value is greater than 1, then it indicates that carbon productivity is rising, which is a very good sign. That means there is a scope that that particular sector is basically going to help in the net zero or in the reduction of carbon emissions. The third alternative case is a lower GLM score, which is basically the carbon productivity is decreasing, which means that for production of more goods and services, these industries are using more of energy sources and hence increasing the carbon coefficient or the carbon dioxide in the atmosphere. Then what we do, we basically decompose it. If you look at here in this index, there are three sub-index that you can look at. One is GML, which is basically nothing but the efficiency change and the technological change parameters. But then the question is, once you get the idea of the carbon productivity based on the calculation of the index that was presented before, then the idea is whether they're converging. So how do we look at the convergence part? We can look at either from sigma convergence, or which is typically the cross-sectional dispersion in terms of the variable of interest, and here the variable of interest is carbon productivity. The second case is there can be an absolute beta convergence, or there can be a conditional beta convergence. So we have basically two classification. One is a sigma convergence, then we have a beta convergence. The beta convergence can be either absolute or can be conditional. Right? So how do we interpret these mathematical equations? If the cross-sectional dispersion of carbon productivity across sector tends to decrease significantly over time, then we say there is a sigma convergence. And the idea of the beta convergence comes from the neoclassical growth theory in case of the absolute beta convergence, and it comes from the neoclassical growth theory with identical structural characteristics from each of the cases that we study in terms of the conditional beta convergence. Now, let me tell you why these things are important in terms of understanding the complexity of carbon productivity, energy consumption, and so on and so forth. So if you look at the standard literature in and around energy economics, energy economists have looked at immensely in terms of understanding the trends and patterns of energy consumption, the pricing of energy consumption, the bidirectional, unidirectional relationship with the growth parameters. They have also looked at the substitution possibilities. They've developed certain methodology like nested production functions, where they're looking at the cost functions of each of the parameters of choice related to energy and energy sources. But what has not been looked at recently is linking energy in a much different way by creating a proxy, which is carbon dioxide, which accounts almost 70% in the greenhouse gas emissions which we care about. And therefore, if a researcher can come up with the idea of carbon productivity, look at the movement across sector over a period of time or within cross sections, or within geographical locations or regions, or even inter-district or even inter-population distributions, then we get to know the existence and the dependency on energy resources, and the respective energy resources, how much carbon emission is going to be linked with it. So therefore, the idea of this paper is first to estimate the emission coefficient from the consumption of energy sources, which can also be replicated at household levels, not necessarily at the level of industry as the case I'm presenting here, and then look at the movement of these emissions in terms of a convergence series, and then come up with an idea that whether they are converging, and if they are converging, then what kind of policy we can think of, and if they're not converging, then what kind of policy that we can think about. Now, what are the key indicators of choice that we can think about? Here, the first indicator of choice, because it's an empirical IO perspective or industrial economics perspective, the first choice variable is firm size. Now, there are multiple industrial economic theories that basically identify why firm size is important, because bigger firms have more resources, bigger firms have larger assets, bigger firms have more knowledge flows, bigger firm can take risk, and large firm generally do not get into the financial constraint. These are majority of the reasons why the bigger firms has been taken as one of the major indicators when you try and understand the industrial economics point of view. The second question is, the bigger the firm, the consumption of energy would be higher, and therefore the emissions would be higher. This is the standard argument that goes, but in presence of technology, the energy consumption may be lower. Or maybe in presence of technological paradigm shift, the substitution of energy may be higher and therefore achieving higher efficiency. And in this case, what we do, we also look at in terms of industrial output from value added. Why value added is important? Because in this particular paper or in this particular project, what we are looking at is output function and the energy function. Now, in a typical productivity analysis, we have four-factor productivity analysis. We have energy as one of the factors. So, not to double count it, we try to look at from the output value added function, not the simple gross sale function, which or gross output production function, which basically people talk about it. It is always better to kind of deviate from the consumption of energy because we don't want to double count that. The third variable of interest is the industrial structure. Basically, how the industrial structure is relative to the existing major industrial structure. That means the presence of a particular sector in terms of the output within the sector itself. What we assume here, we assume that if industry focuses on sectors with high carbon productivity, the structural effect is positive and vice versa. That means if an industry is trying to capture the market segment faster and becoming a dominant factor within the structural effect, then we assume that the carbon productivity would be higher, which is a positive sign for the sustainable economic growth. Then the choice of variable would be KL, which is basically capital deepening in each sector, because we all know that capital as a productivity measurement will have a depreciation values, and it is also difficult for large firms to immediately shift capital, and therefore there is the deepening of capital over a period of time. And then we also talk about the energy consumption structure of each sector, because if you carefully look at the CMI Provis database, which we have used in particular study, there are around 60 to 70 types of energy being consumed in these sectors, and they're consumed on a randomized basis based on the pricing structure, and majority of them are classified into 7 parameters of interest. One is a primary energy consumption, secondary energy consumption, tertiary energy consumption, so on and so forth. But within this entire available information about the energy that the firms consume, coal is majority of them, which has been historically the dependency of energy consumption for a manufacturing firm, followed by the oil, largely furnace oil, and related materials, which generally have high emission coefficient in terms of the carbon dioxide emission coefficient. But within that, coal is one of the parameter which we have taken as a referral case, where we basically convert each of the energy type into a representative of a coal emission coefficient, because that is one of the major emitting indicator of the energy consumption pattern that we have in the industrial segment in India. So an empirical research is not complete without econometric application, specification, limitations, and development. So what we do, we use a panel data. Here the data structure is a balanced panel data, because we need to know the respective changes over a period of time, and we don't want to allow entry and exit pattern in the form, so that it can give a better understanding of the energy problem, and we can basically come up with better solutions. Of course, the limitation would be that we are restricting our sample observations, and an unbalanced panel would give you more sample than the balanced panel. But in this case, we are able to look at the 18 years movement of firms that have repeatedly given financial data as well as energy consumption data for us. Also, it would be interesting to calculate the carbon productivity, because if you remember, we calculate carbon productivity from an index number, and if we use an index number and we do not have repeated samples and it's an unbalanced panel, then approximation or filling the gaps would be difficult, and therefore balanced panel would be appropriate in this case. But then the question in economics largely comes in terms of basic research is endogeneity problem. That how do we deal with the endogeneity problem of variable of interest? Either it is omission of variable or identification error, and etc., which is largely the econometric specification bias. So the first step, what we do, we use a fixed effects, random effects, Hausman statistics for the first test. But to complement the research in terms of looking at the endogenous problem, what we do that we try for a first order differential GMM estimator or a system GMM estimator in terms of the econometric understanding. But between these two, the system GMM estimator is largely appreciated and accepted, because it basically talks about the weak instrumental problem. And the consistency of parameter can be tested using various statistical framework like Sargent test, A/B test for serial correlation, etc. Now, why I'm specializing or I'm specifying the problems due to econometric applications? Because when we target for a policy research that is related to a burning topic like carbon or energy economics, which are directly going to reflective at a public policy, we have to be 100% sure about how we estimate, what are the limitations of the estimations, what are the limitations of the model formulation, so that the probability of coming up with good policy is relatively high. And therefore, it is always better to look at these dimensions when we look in terms of estimating certain parameters through certain models. Now, if you look at the data, of course, data is quite scanty and quite tedious process in this case, because CMI Provis database gives us the balanced information, but again, that's classified into two dimensions. One is the audited financial balance statement of firms. That's basically the financial indicators in terms of the flow variables. Then you have the stock variables from the idea of energy consumption patterns in terms of different units of measurements, and they don't have a similarity in the measurement series. So therefore, what we have to do basically to club both of them together, that each firm have to report in both the cases, one in the input and other in the stock variable, for example, the energy consumption pattern. So again, as I started the presentation, we do not use data for 2022 and the recent years, because we don't want to get into the dip that has come because of the COVID-19 and try to escape from the non-performing manufacturing components in particular time series for 2 years. The data is for 18 years, a balance panel data we have. We classify them into 3 different components. First, the input components, which are largely the capital, labor, and energy. Then we have the desirable output, which is industrial value added. And then we have undesirable output, which is the CO2 emissions. So if you please remember, we started the idea of presenting the undesirable output of a typical firm as a bad output. That means a typical firm, when get into the production economics, is not aware that the undesirable output are associated with the desirable outputs. So that is the contribution of this work in terms of linking all of them together. Now the question is, we don't have any information about CO2 emissions. Then how do we plan for coming up with values for the CO2 emissions? So one easy way is basically we have the reference material from the IPCC in 2006, which tells us and gives us the idea on how to estimate carbon dioxide emission from a standpoint of bottom-up approach by looking at the type of energy being consumed at a firm level. So we use the IPCC 2006 equation, plug it into the CMI database of energy consumption pattern. Before that, we convert all the energy sources into a systematic and a same level of unit of measurement, because petroleum would be consumed in liters, but cubic liters, but coal would be consumed in tons. So therefore, we have a difference in terms of the idea of measurement also, or unit conversion. So therefore, the construction of data itself takes time, because you have to create a conversion series scientifically, which has to be 100% correct. You have to connect the conversion series into the matrix of the energy consumption data. You have to plug in the energy consumption data with the financial series, and also you have to change the financial series from constant current series to the constant series, so that they are comparable across time. Now, once this set of work is done, then the variable of choice in this particular work that I'm presenting right now is industrial output, the CO2 emission in terms of tons, 1000 tons. Labor variable, which is one of the major variable of interest, because we are also talking about the augmented or the conditional beta convergence model, and we have the capital stock. Obviously, for the capital stock, we can look at any paper, any standard paper written about India. It may be Professor Goldar or Professor Arup Mitra, or Professor Kenarayanan, or anybody else, or one of the EPW paper of Roy Chaudhary 1996 is also equally important for us to look at the idea of constructing the variable for capital stock. And we have 1692 of the firm-year observations, and the energy unit of conversion, as I was telling, is basically standard coal equivalent. I could have used British thermal units, but because I'm looking from a coal reference point of view and link it with the emission coefficient, it is standardized form that we can use a standard coal equivalent, which is almost 27.78 million British thermal units in terms of the measurement that comes into picture. Now let's look at the convergence of carbon productivity from a viewpoint of sigma convergence, right? Now, if you look at the estimated coefficient, so what we have done, please look at the GML index, which is nothing but the carbon productivity change, further decomposed into two different characteristics. One is efficiency change and one is technical change. So the interpretation here is the carbon productivity of one is due to 95% change in efficiency and 92% change in technology. That's how we look at the variables. We generally do not explain the efficiency and technical change unless the efficiency and technical change are pretty low. In this case, if you look at, they're above 90%, 95%, 90%, which is pretty okay in terms of the efficiency and technical parameters, which means the firms are getting efficient from 2004 to 2021. And therefore, it's a very good observation that the Indian manufacturing firms are getting efficient in terms of the cost function. So please also look at that. We have a cost function behind running in terms of the econometric specification when we talk about capital productivity and etc. Technologically, the firms are upgrading themselves, which is also that we get 90% and more contributing to the carbon productivity argument. But what is important here is the GML index, which is the convergence of carbon productivity through the sigma convergence. So what has happened is, if you look at the sector, so what I have done here, I have estimated for different sectors, and there is no need of estimating at the full level in this case, because the sigma convergence is the first set of argument that we start and then get into the conditional beta or the beta convergence. So what we see that, if you remember the interpretation that I started with, the idea of convergence, whether that is equal to 1, less than 1, or greater than 1, right? So if you look at the GML scores, basic metals, chemical products, fabricated metals, machinery equipments have been kind of no change. That means they might have achieved efficiency and technological change, but that is not reflecting in terms of the carbon productivity convergence, which means they have increased their cost efficiency, they have increased their technical efficiency, but they have not been able to look in terms of a sustainable parameter of carbon productivity growth. So the impression number one, we must look at these industries and see in much detail what are the factors that drive not being able to reflect in the carbon productivity change. But the major concern comes from coke and refine industries, which are large energy intensive industries, computer electronics aided industries, electrical equipment industries, food product industries, motor vehicle industries, paper product industries, where the GML index is decreasing, which means that carbon productivity convergence is decreasing, which is a major concern, because if it is no change, that it's still okay, because the growth parameter seems to be okay at the basic level. But if it is decreasing, then these sectors need careful analysis of the composition and the metrics of the energy consumption happens in the sector, and what kind of policy and technological parameter these sectors require. We need to go a little bit detail in understanding these sectors, or maybe some primary data would help in this case. Maybe some kind of engagement with the technological or interdisciplinary work can help in understanding why these sectors have decreased in terms of carbon productivity, which is a real concern. But the parts where it looks very promising is pharmaceutical sectors, rubber and plastic sectors, textile sectors, where the carbon productivity is increasing, which means that these firms are able to produce more by consuming less energy and emitting less. So one marker from here is the other sectors can look at from these sectors by adopting technologies in their production process by such a way that they can basically become better carbon productive. I would also like to highlight here one particular very sharp observation in this table. The pharmaceutical sectors are high-tech industries, but the textile sectors are not high-tech industries, but still textile sectors have shown increase in the carbon productivity. That means the technological parameters in the textile sector production economics are rapidly changing, either because of import of technology from other economies or developing technology from domestic economies. So it is not necessary that the technologically advanced production system have achieved carbon productivity, but also in Indian case, we can see that the textile sector is promising. It is equally important to look at this textile sector because Textile sector is also directly linked with the agriculture production and the linkage between the village ecosystem to urban to peri-urban to urban to the big city in terms of the idea of production and value chain system. So the understanding here is the sectors are not behaving similarly. Number one, there are sectors where productivity has gained, there are sectors where productivity has decreased, there are sectors where there is no change in productivity. And this basically becomes the standard estimation process now to further look at what is happening in each of the sectors, which would be done in our next work. But before that, let us look at what happens to the beta convergence. So within the beta convergence argument, if you remember, we looked in terms of the absolute beta convergence, and we also are going to talk about conditional beta convergence. So when we talk about the conditional beta convergence, we are basically creating some more interactive variables in the system of equations where we are controlling for few form characteristics, and in the absolute convergence, we are not controlling for those characteristics. So the results that is presented in this particular table, where we got the fixed effects estimate to be correct based on the Hausman test statistics, implies that there is an existence of absolute beta convergence sectors with low initial carbon productivity, and they're catching up with the sectors with high initial levels and will eventually reach a common strategy, common steady state of growth. How can I conclude on this? Because what has happened is instead of estimating in this way, where we have classified them as in terms of standard sectoral NIC 2008 classification, what I have done in this case is I have assumed that the industrial policy largely affect all the firms, and therefore let us have a classification of the full sample. Then let us look at what is happening to the pollutive sectors and the clean sectors. Now, the pollutive sectors and the clean sectors are classified based on the idea of energy consumption that is classified in terms of the public policy document of which sectors are typically polluting and which sectors are clean sectors. What is interesting to look at here is the beta value. The B value is systematically negative in all these three subsections. Either it is polluting or clean, or even it is in case of the full sample, which means there is an existence of an absolute beta convergence, which is a very good news. That means if we look at the forms or the form growth in terms of the aggregate series, then they are basically converging in terms of a beta convergence, but they are not converging systematically in terms of beta sigma convergence when we estimate them in a silo. That means when you estimate them separately, which also indicate that in this particular table, there may be a possibility that there are firms which are less in number in case of basic metals as compared to chemical products, because we are talking about only a data which is systematically present for all 18 years. The number two case is maybe the market share of these firms would be less, and the number three is competition and the market structure are different for all different sectors that we are talking about. So therefore, in our case, what happens, the beta convergence seems to be a better result as compared to the sigma convergence. Now, if you look at the conditional convergence, which is much better than the idea of the absolute beta convergence, because in this case, what we are trying to explain is we are also taking the lagged series of the productivity, which you can see L1G. L1G is basically the lag series. We are also taking about our structure of the market. We are talking about the capital depreciating idea. We are also talking about the energy dependent or energy structure of the firm. So in presence of these indicators, that means when we control the experiment and we re-estimate in presence of these particular indicators, we are still achieving the beta convergence and conditional beta convergence, because the statistical significance values for logarithmic, natural logarithmic of the carbon productivity of ith form at time t is systematically negative for the full sample, the polluting sector, and the clean sector. Nonetheless, the clean sectors are doing well as compared to the polluting sectors and as compared to the full sample segment. Right. And of course, the test statistics signifies that the results are okay to estimate, and the robustness of the results are achieved based on, if you look at the world statistics, the Ever test and the Sargent test that we have done in the particular estimation series. So what are the impression that I get from these fundamental analysis and the analytical procedure? Number one, we empirically investigate the convergence of carbon productivity, which is one of the first attempt by taking the physical amount of energy consumed in Indian industries, plugging with the financial flows in Indian manufacturing sector. We saw that the result is does not exhibit obvious convergence or divergence over a period of time. That means the sectors are systematically different across time. There is a possibility that time horizon may play a role, and the sectors are not identical with each other in terms of representing a convergence or divergence. That is basically an impression that comes from the sigma convergence. And the sectors with low carbon productivity grow faster than the sector with high carbon productivity, which essentially means that we have to look at the polluting sectors much more intensely with differentiated public policy interventions, with specific targets and with specific idea of technology being implemented, such as, for example, these days, the idea of carbon capture, utilization and storage technology are being developed in a lot of institutions, including IIT Madras, which can be probably converted into from lab scale to the production scale, which will definitely help the high emitting sectors. So moving forward, if you look at the findings of the current research that we have done, we basically look at to rethink, do a lot of more research on carbon productivity, the way research has developed in India in terms of looking at the energy intensity and energy efficiency studies. And we must look at from the view of technological parameters, not necessarily the economic parameter, which are important, but definitely we have to link with the technological parameter. Now, if we want to reduce the reasonable amount of oil and coal, then in the actual production process, then we have to identify high carbon energy sectors and hence look at the segregated amount of policy that we can think about, and hence a singular policy or a central policy would not help, but decentralized policy is definitely going to help. One more, moving forward, an extension is definitely looking at the regional specification of parameters, because the climate conditions are different and hence the requirement of energy sources and the availability of energy sources. For example, the market that determines the energy in India may be different based on the geographical parameter, infrastructure quality, and establishment of certain industries and certain sectors. For example, if you look at the case of Odisha itself, we have heavy manufacturing industries, which are bauxite, aluminum, etc., that would differently behave as compared to a state like Karnataka, where Bangalore has large scale of IT, ITS industries. So we cannot have a similar policies or similar ideas, but what we need to do as a researcher in the public policy domain to look at large scale studies that can basically come up with multiple ideas of differentiated policy and indications from the firm level to the unit level analysis. So in that sense, use of annual survey of industry data would also be highly impressive, along with the use of CMI province data set, so that we can also look at the multi-unit, single unit form characteristics situated in urban and rural pockets. Now, one thing which always we know that India is an energy dependent economy. Our large scale import comes from energy. Therefore, any international fluctuations on parameters have a direct impact on Indian economy. And being we are dependent, or rather we are importing larger from the energy side, we have to think about how we can become energy independent, which leads to the energy security concern that we are relying on, and therefore identifying better and efficient energy sources, such as the hydrogen, which is one of the major game changer would be if the green hydrogen and adoption, production and distribution would happen, then that is going to change the fate of the industrial production system, because we may be able to, we are probably going to be able to satisfy our domestic production of hydrogen and reduce the energy dependency from the import bills. So therefore, this kind of research is going to help us by looking at that how much energy, how much carbon is being emitted by each of the types of energy being consumed, and what are the types of energy that we must reduce over a period of time through technology interventions. And of course, it is advisable to promote cleaner productions, engineering systems in the industrial segment across India in a systematic and homogeneous perspective, encourage firms to adopt and apply advanced technologies, and definitely think about auditing their energy requirement, because energy auditing has to be mandatory in such a case, because there are studies that have confirmed that the education on energy consumption and energy loss in the sense, the conversion of energy which is not an input to a production system, has been pretty low across sectors, and therefore there is a need for educating the labor force in order to think about how efficiently we can use the energy as an input. And unless we do that, we are not able to attain the energy efficiency. If we are not able to attain energy efficiency, definitely we are not able to attain the carbon productivity. And if we are not attaining carbon productivity, we are not going to reduce aggregate carbon emissions from the aggregate economy or sub aggregate economy, and therefore it may become very difficult for us to attain net zero, or even go beyond net zero in different sectors. Given the manufacturing sector has a large contribution for economic growth, employment generation, etc., etc., we cannot forget the contribution of manufacturing sector, neither in terms of increased output nor in terms of contributing to the emissions or consuming high energy sources. So with this, thank you very much for the opportunity, and I'm open for any questions, suggestions, comments on the work that we are doing, because this work is going to be, as the work is in progress, because we are looking at various aspects of energy neutrality and net zero attaining from different sectors and subsectors. So any advice, any critique, any limitation of the study or any questions, I'd be happy to engage with. Thank you very much.
Thank you, Professor Sahu. No, we had really an excellent presentation with utmost clarity of everything. So let us take up some questions from the floor, and then I also have a few questions. I think somebody was already typing.
Yes, sir. So can I?
Yes, yeah, Himja, yes.
Good afternoon, sir. So it was a wonderful lecture, and Dr. Sao is very famous, and I'm also working in this area only. I'm just a budding scholar, and I've read many of your papers since the last decade. I'm following your papers on carbon productivity and all. Sir, I had a doubt. I have read your papers, all recent papers also for IPC 2006 approach. I have a doubt. It says that energy, let's say we are having, because we know that firms are using various kind of energy. Basically one is in solid, that is coal we take, then in liquid we have petrol also, and in gaseous form we have also. I'm very clear about CEV, that carbon emission factor is given, carbon oxidation factor is there, and then we multiply it by 44 by 12, that is IPC. But what about the NCV? Because these three are in different forms. Then how we are actually making it in a single series and then multiplying it by them? Because I read your paper also, that recent one, analysis of carbon productivity of firms in the manufacturing sector of India, that is by you and Pranitik Bagchi, sir. So can you please give me insight of NCV? I was stuck a very long time for this. I'm stuck. So it will be very helpful for me if I'm getting some insight over NCV. Because three kind of, hello? Am I audible, sir? Hello?
Yes, you
Yeah,
are.
yeah.
Yes, you are audible.
Yes.
Yes.
So please, sir, if it will be a great help if you give me insight of NCV, that if different type of fuel are there, how can I make them into a single kind of thing?
Professor Sai, you are mute. Yes.
Okay. No, should I respond as and when, or should I wait for
Yeah, I
questions?
think you can respond so that
Okay.
we have.
So thank you, Kinja, for the question. See, the net caloric value, not only three parameters, but as I said, there are 60 types of energy the Indian manufacturing firms are consuming. Okay. There are 60. Now, the 60 are classified into seven major parameters. But if you look at the data very, very carefully, you won't get 60 entries. Right? You get less than 60 entries. So step number one, each of the fuel that is consumed has to be converted into a common scale. So what is the common scale? You decide as a researcher. You can say kilojoules as a common scale. You can say British thermal unit as a common scale. You can say coal equivalent as a common scale. So that means either you follow SI standard or you follow the British standard. It doesn't matter actually. because we are converting into a common scale, number one. Number two, once it is converted into a common scale, then every element that is consumed, that means fossil fuel. So because the IPCC, the limitation of IPCC 2006 is it has to be computed only for fossil fuels, right? So for fossil fuel, IPCC has given a tabular form where you get the approximate net caloric value for each of them. So you get the value for coal, you get the value for, within coal also you get 5-6 values you get, right? And then you get for natural gas, then you get it for, let's say, any kind of furnace oil, right? So you get 10 or 20 such kind of conversion factors. Each conversion factor have to be multiplied with the kilojoule if you have converted it. So step number one, convert into kilojoule, for instance, or British thermal unit, whatever you are convenient with, whatever you understand from the science perspective. Okay. First, conversion with the physical unit. Second, multiply with the conversion factor globally available in IPCC. If you read the documentation in the appendix, they've given the numbers. Once you do that, then you add up. Then you add up the entire thing, you get the NCV for each of them. Now coming to 44/12, that is nothing but the caloric value, that is the molecular weight of carbon, right? So that's from the standard science point of view, that is being multiplied. Right? So once you do that, then what you are doing, you are converting every type of fuel, may it be solid, liquid, you are converting into how much effective energy it can give you. That multiplied with all other parameter of choice, including NCV, you are able to make the final series of carbon emissions. But I would also suggest you to please read the recent IPCC reports where they have redefined the idea of estimation procedures. They've made even much advanced methodology to estimate little better than what is estimated in this paper. We can still develop, but the only limitation is the values are given for each country. So please refer back to which country you are looking at it, because the quality of coal would be different from India than the imported coals, right? I hope I'm able to answer your question.
Yes, sir. You are very much. I definitely got the insight also, but a little bit one more doubt is there. If you are
Please
okay,
go ahead.
I can ask.
Please go ahead.
Sir, in your paper, I know this webinar is different, but I'm mentioning exact line of your paper only because it's open in front of my screen also. That the net NCV is net calorific value of kth input provided by IEA Energy Statistics for India.
Yeah.
So the NCV is taken from the IEA India.
Yeah, that is International Energy Administration database gives you. So either you take it from International Energy Administration database, or you take it from IPCC, or you take it from somewhere, so that the number doesn't change. So as I was telling, for India, you get only one value. For China, you get a different value. So you have to be very, very careful when you take the data, because the conversion is important, right? Because
yes, sir,
you take a wrong conversion for representing Indian case.
Yes, so only the cases that whatever value, whatever kind of fuel is given, I have to convert it into a kilojoule, let's say, and then I can only multiply CEF and then carbon oxidation factor and other things.
So oxidation factor is also given in that particular report.
Yes, sir.
Kth input means K equal to coal, K equal to oil, K equal to furnace oil. So K is different type of energy being consumed.
Okay, so irrespective of any type of fuel, like solid, liquid, gas, I have to convert it to a single, then only I'll multiply. Okay, thank you, sir.
Yeah.
Subal Danta. So I just want to. I think you have already explained this question.
Yeah.
So,
and the slides are there. In fact, it's a standard DA technique that you can follow, and with some kind of an augmentation being done. And the augmentation is not possible in this talk series to explain each equation. Therefore, I had to leave many equations and come to the final equations. So any standard DEA textbook would help in estimating these things.
Okay. So now, Balakrishna, did you have a question?
Good evening, sir. Is it audible?
Yes, you are.
Yes.
So thank you, sir, for this wonderful lecture related to this carbon production and manufacturing sector. So I have only small query related to this estimation of carbon from electricity. Because few recent studies, they are also estimating carbon from the electricity as well by multiplying through this oxidation factor. Is that a good approach? Because as you know, electricity is a byproduct, you can say, from the coal and many other things you can produce that. So let's say, as you know, most of the factories or the farms, when they produce, let's say electricity, using electricity, they're going to produce certain things. Can you estimate carbon from the electricity? That's a direct question. Thank you, sir.
Yeah, so I mean, you yourself gave partial answer to the question because we generally do not know whether electricity comes from hydro or comes from thermal. So if it comes from thermal, then obviously it is in high intensive energy use sector. If it comes from hydro, it's relatively a good output. Or if it comes from wind or solar, then it may be a good output with a limitation of waste being generated at some point in time. So, therefore, in majority of studies you read, will never estimate the the carbon factor for the electricity generation because big farms usually have captive power plants, and then when they have captive power plants, we are always accumulating from the energy use side, how much energy is being used by the farms. But nonetheless, they also depend on electricity generated and distributed by the grids. So, if somebody has to do an aggregate economy level work, then looking at the generation point of view would help, not necessarily the reported values of financial outlay for electricity consumption. That would be my understanding, because if I know that okay, there are 100 of firms in India which are producing electricity, and out of that 100 firms I know the type of energy being used to produce electricity, then I can definitely calculate the emissions. But that would be individually for the thermal power plant and otherwise. But in a firm level data, when you have the electricity consumption in prices, or electricity reporting through kilowatt hours where we do not know how it is being produced, it will create a bias if you estimate the emission coefficient for carbon. That would be my suggestion. But when competition goes, we try different methodology. Please look at the methodology that you are referring to, and if scientifically, logically, and with economic science that perfectly matches and it reduces double counting, then please accept it and go ahead with the estimation.
And because the recent this RBI study I'm just referring about what they have estimated the details. So actually for that I thought to ask. Thank you for your insights, sir.
Yeah.
Okay, so if there are no other questions, then let me ask a few questions. Actually.
Absolutely, yes.
So there are a lot of questions on the measurement of the pollution and IPCC. You are using actually the method. So then I'm not getting into that question now. When you were presenting the results and comparing basically the carbon emission from different industries, or it's the conversions that we are using, then the metal industry basically had the highest emission, and a few industries like which has high tech, of course within that the textile industry has less carbon emission. So I was just thinking about the textile industry. What I understand, in the recent years, textile industry has started importing a lot of chemicals from other countries. Now, is that affecting actually the because you observe actually a convergence, right, or a reduction of carbon from textile industry. Now, suppose we now import actually those dirty part, or say the highly polluting, component from other countries, and we use only say the component where actually the emission is less. That could be actually one of the reasons actually. Because during COVID-19, when this textile industry, all these industries shut down, I had some interaction with a few friends who are working in the textile industry, and they're telling that India doesn't produce a lot of things, particularly the chemical component, which is used in textile industry, and that all comes from China because it is sold at a very low price. That is one. So is that actually what explains? And other industry that where you were saying, say for example, in pharmaceutical industry and IT industry, obviously they don't use actually the amount of energy actually that is used in other industries. So when we are estimating this convergence, are you estimating the convergence within this industry at a 2-digit or 3-digit level, or you are estimating the convergence across all groups, like 2-digit classification, say whether it is a convergence between metal or or say textile industry. So that is one. And then uh, Yeah, coming to the regional implications, you have already highlighted so for example, Odisha, which has all these metal industries, if you look at the carbon emission in the Odisha has the highest per capita, or not actually highest, but at least I think third or fourth highest per capita carbon emission in the country. No, it's because we have all the metal-based industries. Okay? And so, what will be the policy implication? Okay? And because as a Center for Policy Research, I was just thinking about that. That suppose, okay, now we try to supply metal, metal to the all the other part of the country, but we suffer actually from the pollution. And if you look at also the technology, probably the technology are not changing that fast in these industries actually. So how do we bring in and these issues, and what kind of policy measures actually we can use to reduce emission?
Yeah, so okay, let me start with the first question where the textile was an example. So, okay, so the convergence is, I mean, they are not compared at an emission level. That is number one. I mean, emission is, one of the corrections, if I have said that in the presentation, that it is not absolute emission of each forms, but it is basically the emission as a ratio of your output that is moving, right? So, how much CO2 emission happens and what is the value added? Now you divide these two and then create that index value, and then you say whether they're converging or not. So mathematically, which means there are multiple cases. Number one, high emitting, high production, low emitting, high production. In those combination, it will come. Now, textile comes as a low emission, low production, right? So when low emission, low production happens, but still the emission goes up, but they're able to catch up. So it's a catching up effect in the convergence series that we saw. That textile, being a low tech industry, is also able to catch up with the productivity increase in the carbon productivity scenario. That is number one. You're absolutely true about the technology parameters, because last 4 to 5 years, we have been trying to get data from Tamil Nadu based textile firms through another collaboration that we have at IIT Madras, to have data from the ground level, what kind of technology they use. And they are importing technology, not only chemicals, but they're also importing the production related technology from other countries, because those technology are either not available in India or they are high cost in India. Therefore, they are going for a cost effectiveness. So they are definitely responsive, because the amount of output produced now has increased than the amount of output would have produced in absence of this technology. So that is definitely one of the reasons, and hence that calls for democratizing technology. I mean, that's what I always think of using the word, but sometimes becomes difficult. Can we democratize a technology which can be used by a majority of the firms to achieve a common goal for climate mitigation activities? Then the estimation that is presented in this paper is based on 4-digit NIC classification weighted regressions, not the non-weighted ones, because even if the pharmaceutical companies are part of chemical in NIC. Now, chemical sector is also one of the emitting sectors. It is also high energy consuming sectors. Drugs may not be, or certain pharma may not be, but it starts from the R&D to output, right? So it is also equally energy dependent sectors. But again, what has happened? Output has gone beyond the idea of output that pharma can produce. India has become a market for hospital tourism. Obviously, because of the quality of medicines that we produce, the diversity and the competitive spirit of the industries that we have. So this sector has increased in the output, and other sectors have increased output when increase in energy consumption also happens. So that is the difference between the textile question and the pharma question. And of course, it is weighted for the 4-digit NIC classification 2008, so that we get a settled idea, not basically an independent score of forms represented in the CMI province database. Coming to Odisha and states like Odisha, not necessarily one state, but there are states which are the backbone of what we call development to others. So please, think about this. If Jharkhand, Odisha would stop mining, who will mine? right? And how development would happen in states where probably there is no mining. But the problem is in the policy we always do not want to talk about it. Rather, we want to talk the alternative of this, saying that these states have been high polluting, the BOD level, COD level are reduced, water availability is not there, infrastructure is bad, and such kind of things. So one state or some states are taking the burden to create the material for to create a final goods and services in the value chain of the manufacturing. So if these states can come up with a better pricing strategy for the ores or for the materials that they basically award to the industries, and probably think of post-production cost, including the cost to the environment, right? I mean, where I belong from a place where for industrialization was not there, and today industrialization has created an impact on the climate change. So unless we have the post-production cost with the externality cost of degrading the environment because of the mining activity or because of the industrialization that goes in terms of pure heavy energy dependent and heavy resource dependent economies, then the cost would not increase. And unless cost increases, the benefit to the state will not come in. Or there should be a state policy on how to get an advantage from the allocation of fund from the central budgeting system, not necessarily as a special state or something like that, which is there in some cases, but definitely from the resource viewpoint. For example, there are certain states like Tamil Nadu which are contributing to the renewable energy in India. Wind energy is surplus in Tamil Nadu. There are states like Odisha which are giving away the natural resources, and then the environment is getting affected by that. So therefore, we have to think about the idea of green growth and rethink about the market outcomes from the price behavior. It is not only the factor cost that should reflect in the price, but it should be factor cost plus the negative environment cost that we don't talk about. Then I think the state should also develop higher, because the financial inflow will be higher in such a case, right? I think these are the questions which we have. There is something from one more
Yes,
question.
yes, Dr. Himanshu, very sad to say that Dr. Amartya is no more. He passed
Yes,
away
sir.
at the.
Sir, let us. No, I understand. So let us finish our question
Yes,
and
we'll
then
finish.
we'll get to that.
Yeah, we'll
Thank
have
you,
a
sir.
1 minute more
Yes.
thing.
So, okay, Subal is asking another question, sir. If we want to see a state level analysis of carbon emission, can we measure the carbon emission at a state level? Okay.
Yeah, of course. Why not? We can measure. That's what I was indicating, to use the ASI data, because ASI data gives you the location of the particular plant, and use a similar kind of a methodology to estimate for the state level. Or even at a state level, we have data by ASI at an aggregate form. So at least start with the aggregate work and then look at the disaggregate manners. So I just want to add something which is definitely not linked with what I have spoken here. See, labor economics has been consistently, people are working, and today we see somebody got Nobel Prize in labor economics. Because the contribution has changed the idea of looking how we see the labor productivity and how we see the contribution of labor to production economics. Unless we do research on carbon related activities, we may not have some kind of policy coming out. Unless we do a lot of research and publications through academic engagement, we are not in a position to suggest anything. I mean, look at what the idea of electric vehicle has come, green hydrogen has come in, renewable energy, which people in fact, if I remember, Dr. Das, you can correct me, Odisha was one of the states implementing solar energy long back, but never got into the forefront in policy, because the technological advance, economics research, public policy support was not in aligning with what the government that time was thinking about electric production from energy production from the solar. So that means that unless we do kind of focus ourselves on researching on areas which is hard to do research, it is difficult to come up with public policy. And thanks to Dr. Das, who has been working on this, creating a center where the focus is on creating public policy through DST.
Yeah. Thank you, Professor Sahu. In fact, when we were telling this, I was thinking that probably the eastern part of India, which has a lot of resources, particularly coal, no, they have the burden of the coal. In fact, I would say because if you have these resources and you have basically conflict of interest. If you switch over towards clean sources of energy, then the employment, the revenue that you get from all these resources would actually you are going to lose all these things. So I would say that this is a conflict of interest. And Tamil states like Tamil Nadu, which do not have much resources, I think they have some amount of lignite, but they don't have coal. So they have, I think, all the pressure to actually go for more cleaner source of energy, because anyway they don't have the burden of these dirty sources of energy. So they can easily actually move towards cleaner source. So in fact, we were doing a review of all the eastern Indian states, and we observed that these states are not actually, they are gradually moving towards solar energy, and particularly among the eastern states, Odisha is definitely a leader. But other states like West Bengal, Jharkhand, Chhattisgarh, they are not showing any sign of moving towards cleaner sources of energy.
No, absolutely. See, because the only dependent on energy sectors as employment will not be the solution.
Yeah.
So unless the employment is diversified and generation of employment is diversified within the state, the resource dependent state, the resource surplus states are going to suffer, because only because of coal you have employment.
Yes.
Right. So before we address the problem of RE, we have to look at what are the other avenues we create for employability in those states where the large scale population is only engaged through coal production and related goods and services.
Yeah. Thank you, Professor Sahu. I think we had really an enriching discussion. Your presentation was really an excellent presentation, and there was enough food for thought, particularly the policy implications, because the results that you have shown will actually, we can use actually for a lot of policy implications. So if you think actually we can probably produce a policy brief on that, actually, how what are your findings on the energy carbon convergence or convergence in the carbon efficiency, and what are the implications actually for these industries, and what should the states do. So thank you so much for this presentation and sharing your valuable knowledge. I also look forward to this publication coming up. I think, or is it already part of it?
No. This is not published as of now. So this is so as I was telling, this is a part of the fund that I have received from Energy Consortium IIT Madras.
Okay.
So this is a work that we are doing right now with a new data set that we have started working on, and obviously we look forward to publish somewhere wherever we get a better avenue kind of a thing.
Yeah.
So we have Energy Summit coming in 2023. So where probably I'm going to present this with the industrial experts and industry, so that the industries also know what is happening in the respective domains.
Right. Yeah. Yes. Okay. So with that, actually, we can probably conclude